That's right. Okay. This is, better identify, 203 spraying. Exam4, chapter 9, eventually 10, and the date is 4/19. Okay. Right. Chemical reactions. Okay, everything we've been doing so far this semester is leading up to this point. Learning the vocabulary from the periodic table and how things go together, how to name compounds. Now we're going to look at what they do, what compounds and elements do when they come close together and we get a reaction from them. We don't always get a reaction, but when we do, this is how they do it. We can give the reaction sort of a qualitative pigeonhole, so to speak. And these are the various types of chemical reactions. That sometimes you'll end up with only one new substance. Okay? Sometimes you end up with two new substances. Sometimes the players just swap places from the reactants to the products. And these are various descriptions of them. We're going to go through them one at a time. But we're going to focus on each one of these. And one other thing to remember is that a chemical reaction can fit into more than one category. Okay? So if we have a combination reaction, sometimes we call that combination. It's also a synthesis reaction, where you have a single product that's produced from two simpler reactants. The easiest one to recognize is if these are two separate elements like that, and they make a compound. Okay? But they don't have to be elements. They can be simple compound, and a complex, more complex compound. That's a synthesis. Just the opposite of that is a decomposition. And if we took that reaction as written before, what was it? Calcium sulfide, was it? I think it was calcium sulfide. And we just went backwards and ended up with calcium and sulfur. That would be a decomposition. So in many respects, you can write a synthesis reaction, and then just the reverse reaction is a decomposition. This is a displacement reaction. And generally speaking, the displacement has an element reacting with a compound, and one part of the compound is replaced by the element. So when it does that, it kicks this element out and just replaces it in the compound. Okay, that's a displacement reaction. You can also have the kind where this, they call it an exchange reaction. I call it double replacement. Okay. So basically what happens is the A, well, in this case, they use the X and the Y. The X and the Y just swap places. So you notice that X is with A over here, but it's with B over here. The Y is with B, but it's with A over here. This silver nitrate plus sodium chloride. So we would, in their scenario, we would swap chlorine with the nitrate. Because nitrate is a polyatomic ion, it acts as a unit. The chlorine and the nitrate, we just swap places. So now we have the chlorine with the silver and the nitrate with the sodium. Double replacement. I've made comments down here, but we'll talk about those as we get to them. Here we go. This type of reaction is a combustion. Combustion reactions have one thing in common. They always have elemental oxygen as one of the reactants. Right? We call it burning. So this is a hydrocarbon, hydro for the hydrogen and C carbon. And we react it with oxygen. And when hydrocarbons react with oxygen, they always produce carbon dioxide and water. If the reaction goes to completion. There are certain intermediate reactions, but we're not going to hammer that one today. So they always have oxygen as one of the reactants. So let's see if we can identify the categories, and then we'll talk about, as we get through go through these examples, we may see multiple categories that can be applied to a reaction. All right, we have this one, HNO3, so it's nitric acid. Reacts to produce what? Nitrogen dioxide, water, and oxygen. So what kind of reaction is that? Complex to simple. The decomposition. We're decomposing this one into these three compounds or elements. Well, there we go. Decomposition. Okay, so now we have three different types to identify. So in this case, we've got a compound with an element, and that element ends up in the place where the hydrogen used to be. See, goes up here. And this hydrogen is now by itself. Single replacement. Or a displacement reaction. How about this one? Two compounds make a more complex compound. That's a synthesis or a combination reaction. How about this one? Ammonia and oxygen produce nitrogen monoxide and water. There's that oxygen. Did you know ammonia can burn? You can combust ammonia with oxygen and produce these two compounds. Oops. There we go, combustion. There's one class we haven't got to yet. And let me check myself. Yes, it needs more detail. Because it's a new breed of animal, so we're going to treat it separately. Oxidation reduction reactions. What do we mean by oxidation reduction? Well, let's just define it. What is oxidation? Oxidation is the process whereby electrons are lost So in the process of a reaction, if something loses an electron or more, one or more electrons, that substance is said to be oxidized. Just the opposite of that is reduction. Electrons gain. So in the process of a reaction, if a reactant gains one or more electrons, it is said to be reduced. Okay, how do you remember those? Oil rig. Oxidation is loss, reduction is gain. Okay. I still use that one too. I'll leave that up there. Okay. So now that we've defined our terms, in a chemical reaction, if something is oxidized, something else is always reduced. They never occur separate from one another. They always occur in pairs. Oxidation reduction go together. That's why we include them as oxidation reduction or redox chemical reaction. And the only reason we say redox and not oxred is just it flows better. And then, of course, you have chemical reactions which are not oxidation reduction. Right? You have the reaction, but there is no transfer of electrons. So I'm going to show you how to tell whether electrons have been transferred. These are clues that you can use to identify a redox reaction. If you have a reaction with an element on one side which becomes part of a compound in the products, or vice versa, if it's part of a compound on the reactant side and it becomes a product element, then that's always oxidation reduction. Okay. Okay, I'll point that out again later. So in order to tell if electrons have been transferred, we need a way of bookkeeping, a way to keep track of our electrons so we know when they've moved. And one way to do that is to identify the oxidation state of each element. What do we mean by that? Well, in general, the number represents a charge, but it may not necessarily be an actual charge. This is just a bookkeeping scheme. We treat it as if it's a charge. Okay? And we have to do that because if it's a charge, then we know that an electron has either been gained or lost. If you start neutral, in other words, if the element has the same number of electrons in it that that shows in the periodic table, then we know it's neutral, right? Because protons and electrons are equal. But if we find that it has an oxidation state of -1, which we call a charge, then we know that it's gained 1 electron. Okay. So how do we tell what the charges are? There are some that we just take as standard. In other words, if there's a compound that has a halogen in it, the halogen is considered -1. Of course, if it's a diatomic like this, chlorine at room temperature and pressure, it's going to be this form, then that has no charge. It's elemental. But if it's in a compound like table salt, this one is -1, and the sodium is +1. All alkali metals in that first group are +1. All halogens are -1. So we can just take those to the bank. Okay. all alkaline earths in the second group are taken as 2+. So magnesium in a compound would be 2+, and of course chlorine is still -1. Okay? So if we start out with, say, magnesium, and then we combine it with chlorine, and we get that compound, right? We know that elements are always 0, right? So if magnesium is 2+, what happened to magnesium? Let's see. Oh, that's balanced. What happened to magnesium? It lost 2 electrons, right? So it went from here to here, 2 electron loss. How about this one? So the chlorine is -1, but it's 0 here. So it had to gain 1 electron per chlorine, or 2 electrons. Okay? That's our bookkeeping scheme. Also notice that when you get through with your bookkeeping calculations, the number lost has to equal the number gained. Otherwise, you did something wrong. Let's see, this one's kind of fading. Look at it. Yeah, let me try this one. Okay. This statement just says that the more electronegative atom generally gets the electron transferred to it, and the less electronegative atom is the one that loses. And in general, the less electronegative is going to be a metal, and the more electronegative is going to be a nonmetal. Did we talk about electronegativity yet? It's the tendency of an element to draw electrons to itself. So the higher the electronegativity, the stronger the pull on electrons toward that atom. Okay, so these are the rules in statements. If you've got an element, the oxidation state is 0. It has to be the element in its natural state at 1 atmosphere pressure and room temperature, 25 degrees. It's generally taken as room temperature. If you have an ion as part of your reaction, then the monatomic ion, so it's just one atom, then its oxidation state is its charge. In that case, the oxidation state is the charge. So there's no ifs, ands, or buts about that one. I gave you the oxidation numbers for the group 1A of the alkaline metals. They're always +1. Alkaline earths are always +2. Hydrogen is usually 90% of the time +1. So if you have a hydrogen in a compound and you don't know what to give it a +1. -1 is possible, but rare. Well, here we go. Then if we go to the halogens and move to the left one, everybody in the chalcogens, or the oxygens, is generally given a -2. Oxygen is always -2. Sulfur, our first choice, is -2, but it could be others. So if sulfur's in there and you have other elements from the first, second, or the halogen group, or oxygen, then you go ahead and give them their oxidation states right off the bat. And then if sulfur's part of that, and it's the only one left, then you calculate to see if it's -2. Sometimes sulfur can be actually could have plus 4, plus 6 are possible. Right, so that's why oxygen is given -2 all the time, except for one situation where you have peroxides. Everybody knows hydrogen peroxide, right? You keep it in your medicine cabinet. It's 2 oxygens linked together, and then each one of those oxygen has a hydrogen. This part right here makes it a peroxide, where 2 oxygens bound together. This is hydrogen peroxide, but if you have some other group here and some other group there, it's still a peroxide. And the charge on both of these is -2 together. So that means each one is -1. That's why this exception is given. If you have peroxide, then you just count the peroxide as a -2 together. Okay. Then if you have a binary molecular compound, and what we mean by that is covalently bound, that it's not ionic. Sodium chloride would be an ionic compound. Water would be a molecular compound. Right? So if you have like that, then oxygen is going to be -2, and each one of these is going to be +1. Right? So you add them all together, they're neutral. Right? And that's also another rule. The oxidation states on each of the atoms in the compound has to add up to the charge on the compound. So if it's neutral, they have to add up to 0. If you have something like this, a polyatomic ion with a charge on it, then you have to add them all up to -1. Right? So oxygen would be -2 times 3 would be -6. Right? And we have to hold out one of these minuses for that charge. So -5 is the one that has to be balanced. Right? So -5 would make this one +5. Right? So +5 plus 6 for the oxygens is -1. So that's an example of polyatomic ion. You have to add up to the charge on the ion. Okay, so let's look at the oxidation numbers for each of the following. K2Cr207. Okay, potassium dichromate. What are the oxidation numbers for each one? Well, potassium is first group, right? Alkali metal, so it has to be +1. And 2 times +1 is +2. Right? So that's assigned to the potassiums. Then the oxygens are always -2. So 7 times -2 is -14. Okay, total for the oxygens. Now we can calculate what chromium is, because chromium can vary. So what's the difference between -14 and +2? -12. Right? So the chromiums have to balance this -12. That means the chromiums together, both of them, have to be +12. And each one then is +6. So the oxidation number for chromium in this molecule is +6. Okay. And you can check yourself. Just add them up. -14 and +14 is 0. So we're good. How about this one? Polyatomic ion, so this one has to add up to 2 minus. So we know what oxygen is. So oxygen is -2, so that's -6 total. And then we've got to hold out 2 of those minuses for this one right here. So that means we've got to balance -4 with carbon. So carbon is +4. Okay? Here we go. +4. How about manganese dioxide? Where do we start with this one? Start with the one you know. Oxygen is -2. So a total of -4. Molecule's neutral, so we balance all those -4s with this one. +4. PCl5. Now, PCl5 is a molecular compound. It's all shared electrons, right? Because phosphorus and chlorine are both nonmetals. But we still treat them as if they have charges, even though they don't really. So chlorine is -1, so that means -5 total. That means with only one phosphorus, that phosphorus has to be +5 to balance it. Okay? How about sulfur tetrachloride? Which one do we go to here? I go to the fluorine first, because halogens are always -1. So -4 has to be balanced. That means sulfur has to be +4. There you go. Okay? Okay, so now that we know how to use oxidation numbers, we can calculate them for reactants and products. And of course, these are elemental. Calcium and chlorine are both 0. But over here, chlorine is -1. And since there are 2 of them, the calcium has to be +2. So we know that calcium has lost 2 electrons per calcium. Chlorine has gained 1 electron per chlorine, which means 2 total electrons. See how that is? All right, so if both of these are 0, and this one's 2+, and this one's 1-, then the calcium has lost 2 electrons per calcium. I always write it that way. And then times however many calciums you have, 1, is 2 electrons there. And then for this one, we're going from a 0 to a -1 on the chlorine, individual chlorine atoms. So they gain 1 electron per chlorine times 2 chlorines equals 2 electrons. So that's how I keep myself out of trouble. Bookkeeping wise. All right. Now we just did one of these. Let's go to the next one. Okay, one thing I didn't discuss was this extra term. Whichever one is oxidized is the reducing agent. That is, it is the one that supplies electrons for reduction of the other one. Right, so if you've got something that's being oxidized, then it becomes the reducing agent, and anything that's reduced becomes the oxidizing agent, because it's the one that accepts the electrons and draws them away from the other one, causing its oxidation. There's your oil rig. Well, Okay, let's see if we can define which is oxidized and which is reduced. And it's still on the board. Okay, oxidation state for copper, 0, right? It's an element. Oxidation state for silver is also 0. Okay? Now, the nice thing about these types of reactions, if you have a polyatomic ion on both sides, and it hasn't split up anywhere, then for our purposes, we know that there's no change in the nitrogen and oxygen from one side to the other. That means we can just say that whole group, -1, -1. So nothing has happened to the nitrate. Everything interesting that happens is with the copper and silver. So if this is -1, silver has to balance it with +1. And if this is -1 and there are 2 of them, that means a total of -2. The copper has to be +2. Okay? Now what's happened? Well, the copper obviously changed from 0 to +2, so what did it happen? Lost 2 electrons per copper. And the silver went from +1 to 0. It had to gain 1 electron per silver times 2 equals 2 electrons. We're balanced. This one is the loss, oxidation. This one is the gain, reduction. Okay? And this one's the reducing agent. This one's the oxidizing agent. Now, let's see if we can figure out which one of these is right. Copper is oxidized. Is that true? Yes. Copper was oxidized. So that means it's got to be A or B. Copper is the reducing agent. So if it's oxidized, it is the reducing agent. Silver nitrate is not the reducing agent. It's the oxidizing agent. Okay. Back up. Okay. It's touchy. You stop me anytime if you need further explanation. Let's see if we can define which one of these is an oxidation reduction reaction, which one's not. Right? So for A, we have zinc plus hydrochloric acid yields what? Zinc 2 chloride plus hydrogen gas. Is that an oxidation reduction reaction? We can go in and do the oxidation states on each one and show that this is an oxidation reduction. But if the question is just oxidation reduction, well, there is more to it. You're right. This. Which is the oxidizing agent? Which is the reducing agent? So first of all, we can say this is an oxidation reduction reaction because there's an element here that's part of a compound here. So that clue tells you that it is. So we go ahead and do our accounting. -1 for chlorine, +1 for hydrogen. Zinc now, since this is -1, and we have -2 total, this one has to be +2. And this one is 0. So which one's which? Zinc is oxidized. And hydrogen is reduced because it gained electrons, right? It went from +1 to 0. So this is an oxidation reduction reaction. Which one is the oxidizing agent? The one that's reduced. So hydrogen chloride or hydrochloric acid is the oxidizing agent. That makes zinc the reducing agent. Okay? Let's see. Oops, gave that one away. Zinc is a reducing agent. HCl is the oxidizing agent. This one is not an oxidation reduction reaction. All you have to do is go in and determine what are the oxidation states for each one. Oxygen and hydrogen did not change from there to there. Dichromate ion becoming the chromate. The chromate is still +6, right? 4 times -2 is -8. -6 has to be balanced to leave 2 extra, so that's +6. And we just did this from before, it's +6. So this reaction is not an oxidation reduction reaction. It happens, but it's not oxidation reduction. Whereas this one is, right? You have copper in here in a compound, and over here it's an element. So copper went from +1 to 0. It had to gain an electron. That means it is reduced. It is the oxidizing agent. Oh, let's do this one. This is a funny one. Notice that we've got this one, and it becomes, copper ends up in 2 different places. Right? So if copper is +1 here, then over here it's +2, and over here it's 0. Okay? So since there are 2 up here, one of these coppers went from here to here, oxidized, and the other one went from here to here, reduced. So that means copper 1 chloride is both the oxidizing agent and the reducing agent, as written. But we know that one molecule does one thing and the other molecule does the other. Okay? This is called disproportionation. Disproportionation. And it's the way that some copper ores are purified. In other words, you get copper metal out of this process. You just heat it up, and it reacts with itself and produces this one here in copper metal. You get the metal out, and then you take this one and do a further reaction to get that copper out. But that's the first step in refining copper, if copper chloride is part of the ore. Sometimes it's copper chloride, and sometimes it's that plus something else, like copper carbonate. I don't think copper nitrate is common. It's probably a carbonate, sometimes phosphates. You have to talk to a mining engineer to be sure. That's not my bailiwick. Okay. So we're going to talk about chemical reactions in terms of theory, actually. And remember, a theory tries to explain why something happens. In other words, and we need a model. Right? So theories always have an explanation of why and a model to show us how that happens. So this model, the collision theory for chemical reactions, does a pretty good job of explaining how a chemical reaction occurs and why it occurs, or why it doesn't occur as frequently as we would expect. So the first thing that's required is that molecules have to collide. In other words, you're not going to get a reaction unless at least two molecules bang up against each other. They have to be close before you get a reaction. Right? And then if they collide, they have to have enough energy to precipitate the reaction. So why do they need that extra energy? Well, think about it. Particularly if you've got a compound that's entering into a reaction. You've got to break bonds before you can reform them in the products, right? And that takes energy. So you have to supply enough energy. Sometimes that's in the form of heat. In other words, just raise the temperature. Means that you're going to have more energetic collisions. Sometimes all you need is a certain wavelength of light, and the light will supply the energy. But that activation energy can be measured, and it's usually given the symbol like that. Now, suppose you've collided, you got enough energy, but the bonds that need to be broken and reformed are on the opposite side of the molecule, right? It's not oriented properly. So that reaction will not occur. They just bounce off each other, nothing happens. Right? So you need proper orientation during the collision in order to get the bonds to break and reform to give you the products that you're expecting. Okay, mentioned that already. Mentioned that already. And this is like a picture diagram. I think it comes out of your book. So with the proper orientation, with the collision and enough energy, notice that you get these two combining, forming a bond, and they also break that bond right there. So then you have just this left over right here, and this forms the new compound, carbon dioxide. If they come together like this, no reaction. If they come together like this, no reaction. Come together like that, no reaction. This is the proper orientation for that collision. So from a probability standpoint, you have 1 chance in 4 of having the proper orientation. Okay, 3 factors necessary for chemical reaction. Well, we need the right temperature, which is one way to get that activation energy. You need frequent collisions, and you need orientation. So you need the collisions. A lower activation energy would be good, right? Lower activation energy means more of the molecules are going to have sufficient energy. If you have high activation energy, And at this temperature, there's only a few of them that are available for reaction. But if the activation energy is here and you have this temperature, enough energy, then a lot more of them have sufficient energy to react. And then you have to have the proper orientation. This other stuff is fluff. It's meant to confuse. Okay. Another characteristic of a reaction. Chemical reactions in which energy is released during the reaction are called exothermic. That is, they give off energy. When we talk about reactions, and in fact, when we talk about any type of chemical system, we have systems and surroundings. The system is whatever we think it is, or sometimes the reaction tells us what the system is. Right? Like Bunsen burner. Right? When you have the flame formed, that's the system, that flame, where you've mixed oxygen and methane together, natural gas, and you get the reaction right there in that flame. Right? So, if heat leaves the system during the reaction, then that's exothermic. But if during the reaction heat is absorbed, that's endothermic. It comes from the prefixes, the Greek prefixes. Exo means to exit, and endo means go into. And thermic, of course, refers to heat. And if you have numbers assigned to it, and we can assign values to how much heat is either being released or absorbed, then it's all in reference to the system. If it's endothermic, then heat is being added to the system, and that's a positive value. If heat's leaving the system, relative to the system, it's losing. So that's a negative value. Okay? It's just conventions. It's all as the system sees it. Okay, so what does that look like on a graph? If we graph the progress of the reaction on the x-axis, it starts here, ends over here. Okay? And this is energy, or the heat, either one. The total energy of the reactants would be your starting place. So in this case, we're starting high. Total energy of your reactants. And you can calculate that also. Then we add energy to it to get the reaction to go, because if the reactants are sitting over here, they're not doing anything. They're just there, they're just sitting there, doing nothing. If we add energy to that during the progress of the reaction, then we reach a point where we have enough energy to start the reaction. And that difference between here and here is the activation energy. And once you reach that point, the reaction goes on its own. In this case, these are the products, and the products have less energy than the reactants. Okay? So that means we released some energy. It's like the energy is stored up here, and down here, since there's less here, it's been released. So this difference here is the change in energy, delta H, and it's going to be, since it's leaving the system, it's going to be a negative value. And you can think of it this way. This one becomes less, so it's become more negative. And this is an exothermic reaction. Okay? Now, you could start over here with your reactants and end up over here with your products. That would be an endothermic reaction. Right? Or you could run this reaction in reverse. What if we started over here and called these our reactants and ran back that way? What would the activation energy be then? The activation energy would be the difference between the products and this activated state. So for the reaction in reverse, the activation energy would be huge. Right? You had to put a lot of energy into it to get it to go back over here. That's what happens when you make nitroglycerin. Right? The energy of the reactants is less than the energy of the product. So you have glycerol, and you have nitric acid, and a little bit of sulfuric acid to help the reaction, but that's not part of the reactants and products. And then it gets hot, you heat it up, it goes like that. It produces a product, nitroglycerin, that has a lot of energy stored in it. It's an endothermic reaction. And in the process, you've got an explosive. But this activation energy up here for nitroglycerin is very small. Way down here like this. So once you get over here, you don't even want to bump that nitroglycerin because it will go and release all that energy. You just look at it cross-eyed, and it's got enough activation energy to go. So these values can vary depending on the reaction. This is just a generalized description of what's happening during a reaction. Plants have been using this process forever. Photosynthesis is a process whereby the plant takes energy from the sun, stores that energy in molecules like sugars, complex carbohydrates, celluloses, lignins for their cell walls, and they use it to make the other things that they need, proteins, for instance, their enzymes. Those are all endothermic reactions. They take that energy from the sun and store it in their molecules. And then animals come along and eat them. And they convert that energy into something useful. So when animals eat the plants, most of those reactions that we generate, at least in the digestion process, are exothermic. They release the energy, and we take that energy and use it to do other things, like build our own proteins, build our own carbohydrates, build our hormones, whatever. So it's all an energy play. And most of the energy that comes from the sun. Not all of it, because there are some reactions that are chemosynthetic. Right? You've heard of the deep ocean vents, those hot vents along the mid-ocean ridge in the Atlantic. They've got bacteria down there that use the heat and products coming out of that vent as their energy source. So they're completely isolated from the sun, but they still use that, and they use that energy to do things. And then those tube worms, they have a symbiotic relationship with those bacteria, and they use the products that they make to do their thing. Okay, so it's a whole community down there. It's actually an ecosystem. Okay. So this is what the reaction would be for an endothermic reaction. Right? The energy of the reactants is much lower than the energy of the products, but you still have an activation energy in this case, which is huge by comparison. Let's see, during an exothermic reaction, the average energy of the products is higher than the average energy of the reactants. Is that true? It's the other way around. During an exothermic reaction, the products have a lower energy than the reactants, because if they have less energy after the reaction, it's got to go somewhere exothermic. So A is false. During an endothermic reaction, the average energy of the products is lower than the average energy of the reactants. That's just the opposite. These two need to be switched, parts of them, to make them true. So during an exothermic reaction, the average energy of the products is lower than the average energy of the reactants. C is true. A and B are false. And consequently, D is false. Okay. So we talked about types of reactions, whether the energy goes into the reaction or comes out of the reaction. How to tell if it's a redox reaction. Now let's say a few things about reaction rates. Because how fast a reaction proceeds actually depends upon the activation energy. And the temperature, or the energy that's given to the system to make the reaction go, will determine the reaction rate. Sometimes reactions, we say the reaction is spontaneous. That means when you put the reactants together, they just go make products. But that doesn't say how fast they go. So this study of reaction rates is called kinetics. Okay. So what affects the rate of reaction? Well, it just could be the physical nature of the reactants. In other words, if the collision theory says that they have to bounce into each other, then if one's a solid and the other one's a solid block over here, it's not likely they're going to get together unless you push them together, and then they're only going to have contact along that surface, right? So if you have two solids, the best way to get reaction rates to increase is to grind them into fine powders and then mix them together, right? So you can have charcoal, saltpeter, and sulfur in 3 piles, nothing happens. Grind them up, mix them together in the right proportion, and then exceed the activation energy with a little spark, and you get gunpowder. Okay? The concentration of your reactants also will increase the reaction rate. In other words, if you have, say, 2 gases that are going to react, and they're in this bulb, but the pressure in the bulb is like 0.01 atmospheres, very low pressure, and that's combined for the 2 reactants in there, they're not going to encounter each other very often, right? So the reaction rate is going to be low. But if you start pumping those in there till you get maybe 100 atmospheres, that means you put more in there to make the pressure go up, then there's going to be more frequent collisions, reaction rate's going to go up. Now that's true not just for pressure concentrations, but for, say, you have solutions that you mix together. So the molarity of the solutions, as it increases, will increase the reaction rate. And then, of course, the temperature. And the reaction temperature refers to the activation energy, right? If you increase the temperature, then more of your molecules have sufficient energy to react. that will increase the rate. In fact, you can actually calculate the increase in the reaction rate if you know the activation energy. But that's not part of this course. And then another way to make the reaction go is to provide it a different route. Okay? One type of air pollutant is given that oxides of nitrogen. This could be 0, it could be 1, 2, 4. Those come out your tailpipe if you don't have a way to convert them, right? So they will eventually convert to this, something else. But we want it to happen faster. So what do? Well, we pump this through our catalytic converter. And on these ceramic beads, we have platinum and palladium coating the surface of those beads. It doesn't take much. You just need a very thin layer around those beads. And as this passes through, it converts it to nitrogen and maybe oxygen or water. It's got some other things in there with it, right? That's the catalyst in your catalytic converter. The reaction goes faster because of the catalyst. And the reason it goes faster is it provides an alternate route. Making this into this by one way would take years. But going through here and providing it another way on the catalyst gives it a different route that goes in milliseconds. Okay? Oh, I didn't realize I had these slides that I could talk from. The physical nature. So the physical state, that's what we're talking about here. Solid, liquid, gas, or particle size. Right? Gas, particle size for gas doesn't mean anything. Right? But for liquids and solids, particle size has a value. Oh, that's one I didn't consider. Dust explosions in the mines, right? You probably already know that if you've got a relative that works in the mines. They constantly monitor the concentration of dust, coal dust in the mines, because being finely divided like that, with oxygen around, that reaction can proceed very fast. And if you get a build up to a certain point, all it needs is a spark, and boom, you get a release of a lot of energy. It's exothermic. In an enclosed space, right? So that shock wave goes traveling down the shaft and kills anything in its path. Concentrations, we mentioned that. Let's move on. Reaction temperature. The speed of the reaction generally increases. Back up. Increases with temperature simply because it increases the number of molecules that have sufficient activation energy to proceed. And then a catalyst, of course, gives you an alternate route to the uncatalyzed pathway. Now, in living systems, they're chock full of catalysts. We call them enzymes. The enzymes are catalysts, but they're more than catalysts. Enzymes don't just speed up the reaction, they control what can react, what can't react. In fact, some enzyme systems are so specific, they only go one direction. So if you wanted to go back, you got to have another enzyme to go back the other direction. That's how controlling they are. So, this is a very simplistic description of enzymes as catalysts. Because yes, they do speed up the reaction, but they are much, much more than that. So what happens with a catalyst? Actually, what happens with a catalyst is it decreases the activation energy. Right? So with the catalyst, you have a lower activation energy for the reaction as opposed to an uncatalyzed reaction. That's why the reaction speeds up, right? For the same reason, well, not for the same reason, but if at a certain temperature, you will get a certain speed of the reaction. But if we lower the activation energy, that means more of your molecules now have sufficient energy to react, right? So that speeds up the reaction. Okay, we increase the rate of the reaction with a catalyst by decreasing the activation energy. Now, that was kinetics, the speed of the reaction. And in my general chemistry class, we always study kinetics first. Because once you understand kinetics, equilibrium discussions become easier. Equilibrium just means that in a chemical reaction, you have reactants yielding products, but the reverse reaction is also possible. And once your reaction reaches equilibrium, you have a certain amount of product and a certain amount of reactant, and they're going backwards and forwards. But looking from the outside, the amount of each one appears to not change at all. That's the macroscopic view. But if you go down, if you get really tiny, and go down and look at the reactions that are occurring, this one and that one are occurring at furious rates. That stuff is happening, the rates. So the rate of this one and the rate of that one, forward, reverse. At equilibrium, these two rates are equal. It's reached a balance point where this one balances that one. That's equilibrium. Now, of course, when you first start off, if you have reactants, in this case hydrogen and iodine, forming this product, when you first start off, the reaction's all one direction because there's nothing over here, right? But eventually, you get enough of this over here that starts going backwards, and they meet in the middle. And this is the equilibrium state. So the reverse reaction eventually catches up with the forward reaction, and now we're at equilibrium. Okay. Another way to look at it is concentration. Right? So for this one, the concentration of hydrogen iodide is your product. So in the beginning, the product is 0, but eventually it increases like that. And the concentration of the reactants start off here, but eventually they decrease to a uniform level. And now we have our equilibrium state. And looking from the outside, it looks like nothing's changing, right? You've got this amount here, this amount here. You know, for all intents and purposes, you're thinking, well, nothing's happening. Right? They're just sitting there. What do we mean by a reversible reaction? Well, this is kind of a reversible reaction is one that can go in reverse, right? And if you shorten the time frame down to an infinitesimally small amount, all reactions are reversible. Right? We decrease the time interval to such a small degree, then every reaction is reversible. But if you make a practical time length, depending on the reaction, then some reactions are reversible and some are irreversible. That is, they basically only go in a forward direction. And what that means is that this part of the reaction is dominant. In fact, it's huge compared to this. Okay? That's what an irreversible reaction is. The reverse is so slow that for all practical purposes, it doesn't exist. Okay, so the state of chemical equilibrium is reached when the concentrations of all the reactants and products remain constant. Okay? And a reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants occur simultaneously. All right, so let's consider this reaction. Water and carbon monoxide producing hydrogen gas and carbon dioxide. We're getting into concepts now that are going to be useful for next week. And they come under the heading of Le Chatelier's principle. Le Chatelier was a Frenchman, obviously, in the middle 19th century. And he proposed that when a reaction has reached equilibrium, once you have equilibrium, then anything you do to disturb that reaction will be responded to by the system in such a way that your disturbance is minimized. Okay? So what do we mean here? Well, if we have this reaction producing hydrogen and carbon dioxide, I'll let the gas part out. Once it reaches equilibrium, what if we add more water? Okay, we add more of this. What happens to the reaction? According to Le Chatelier, if you add more of this on that side, it's going to respond to consume some of that until it reestablishes equilibrium. Right? So it's going to use up some water. Consequently, it has to use up some more carbon monoxide to produce more hydrogen and carbon dioxide until the forward and reverse rates have stabilized again at an equilibrium. Okay, that's Le Chatelier's principle. What if we add more of this? Right? So we're back at equilibrium, and then we're going to add more of that. What happens to the reaction? It goes that way until equilibrium is reestablished. Now, as you may have guessed, equilibrium can be quantified. In other words, at a specific temperature, the temperature is constant. And we can write an expression for this reaction that is always constant at that temperature. And let me use the generic first. So if we have reactants, we have this many A's, this many B's, in equilibrium with this many C's and this many D's. Okay, so these are your coefficients. They'll be numbers. Then our equilibrium expression takes the product, and I use square brackets. Square bracket means concentration at equilibrium. Okay? So that will be C to the coefficient power times D to its coefficient power. That's in the numerator. The denominator then is this to its power and B to its power. That's the equilibrium constant expression for that generic equation. Okay?
What did you say the brackets before?
These are the equilibrium concentrations, right? So if you put some of this in there and none of that, then you can't use that concentration yet. You have to wait until it reaches equilibrium and then measure the concentrations of each one of them to fill in these values. You can use expressions for what's the concentration before you reach equilibrium. In that case, the convention is, instead of square brackets, we just use parentheses. So if you see that, parentheses instead of square brackets, you know it's not equilibrium. Oh, there you go. Well, I use different. WX. That's a bad slide. I need to fix that one. I need to fix and make it look like this one. I think that makes more sense. Easier to follow. Now, this K can have subscripts. Generally, KEQ will be an expression. And usually, if it says KEQ, these concentrations will be in molarity, like moles per liter. For liquids, you can even have molarity for gases. If you have so many moles in a liter space, you can say molarity. Right? But we could write this in terms of partial pressures. Like, if those are gases, we could say K sub P for partial pressure, and then it would be the partial pressure of C to the C power times the partial pressure of D to the D power divided by partial pressure of A to the A power times the partial pressure of B to the B power. Okay? But these numbers are not equal, right? Because we're using different units of measure. But they are related. I don't know if we're going to get to that calculation, but just to illustrate the point, you don't have to use concentrations and molarity. You can use partial pressures if they're gases. If they're not gases, let's see, for gases or solutions, in our case, the aqueous solutions, use values. But if you have a pure liquid or a solid, those are not placed in the equation. Why? Let's start with solids. If a solid forms during a reaction, what's its concentration? It's just a solid. It doesn't have a concentration, right? That's why we leave it out. And for a similar reason, if we have a pure liquid form, it doesn't have a concentration either. Usually that would be, or commonly, a reaction that produces water as a product would not be included in the expression. Hang on to that thought, because when we get to acids and bases, I'm going to come back to this. Okay. Square brackets, okay. Products are always in the numerator, reactants are always in the denominator. And the coefficients become the powers. Okay, we've covered that already. We only use gases and solutions. Pure liquids, pure solids are never included. Okay? So probably what we need is an example. Give us an example. I'm not going to give us an example. Okay. Hold on a second. Let's see if I can think of one. How about zinc plus hydrochloric acid yields here, it's aqueous. Let's see, I ran out of room, so come down here. And hydrogen gas. Okay. The equilibrium expression for that would be, don't use that one, that's a solid. But this is a gas, and those are two aqueous. So we can put those in here as, let's see, I need to balance it first, excuse me. Two hydrogens, two chlorines, one zinc. There you go. So that's to the first power, right? So we don't have to write it. And this one to the first power. In this case, we would need molar concentration of the hydrogen gas. And then this one in the denominator to the second power. And that one is not included because it's a solid. That would be your equilibrium expression for this reaction. Now, when a number is produced over here, right, some number, we never put units with it. The reason being that with powers and different terms from a reaction, the units are all over the place. You know, if you go to a reference manual and look up the K value for a reaction, we won't have any units. If it did, you would have the numbers over here and the units strung out over here over most of the page. It would be a mess. So we just are real careful with writing our balanced equation, our equilibrium expression, and then the number assigned to it. And the units, if you do that properly, then the units take care of themselves. Okay. So what happens to our equilibrium constant if the temperature changes? We talked about concentration, right? If we add more of this, then it's going to shift this way. But in equilibrium, what happens? Well, it shifts until you reach that constant. Remember, this is constant at a temperature. So that means that this concentration times that concentration divided by this one squared is always a constant. So even though it shifts, that stays constant at equilibrium. Right? So this is the equilibrium expression, but if we add more of this, then it's going to use up some of it, but not all of it. That gives us different concentrations for these values that go into the expression to give us that constant. And what we've done is we've changed the equilibrium position. There's a difference between equilibrium constant and equilibrium position. Since the ratio is always constant, you can change this amount as long as this amount keeps up with it, right, to make that constant. So the position and the constant are two different things, related but different. Okay, so what happens? We've talked about what happens if you artificially change the concentration. Right, Le Chatelier tells us. What if you change the temperature? How do we deal with the temperature? Well, in order to talk about disturbances in temperature, the reaction rate, we know, changes with temperature. You increase the temperature, you increase the reaction rate. But what about the equilibrium position? What about the equilibrium constant? The best way to think about equilibrium and temperature relationships is it endothermic or exothermic? And the heat or the temperature, we use them synonymously in this case, determines whether it's part of the product or part of the reactant. Exothermic means part of the product. It gives off heat, so heat is a product. Endothermic means that heat is part of the reactants. It goes into the reaction and is consumed in the reaction. So when you look at it that way, what happens if you increase the temperature for an exothermic process? Well, Le Chatelier says you increase this, it drives the reaction back. So exothermic reactions, if you increase the temperature, you're going to make more reactant. Endothermic, if you increase the temperature, you're adding more reactant, and that makes more product. Okay? Okay, so once we've established what the K value is, what can we say about that K value if it's very large, much, much greater than 1? If it's very large, that means we're favoring products because they're in the numerator, right? That makes them large, the denominator small, so this favors, at equilibrium, favors product. The other case, if the equilibrium constant is less than 1, a lot less than 1, we're favoring the denominator versus the numerator. So this favors reactants. Now some books will say, what if KEQ is equal to 1? And they're going to say that if it's equal to 1, then you have a balance here between equal amounts of this to that, but that ain't the case, right? Because you've got powers to deal with. So it's not always equal to 1 that gives you equal amount here and equal amount there, right? But we can say if it's very much larger than 1, we favor products. Smaller than 1, we favor reactants. That's true. Okay, let's see. We ought to be getting close. Okay. Yeah. We're covering a lot of ground in one chapter here. That's just the nature of a one-semester chemistry course. Oh, okay. So I do have a slide on it. Equilibrium position. The equilibrium position is the qualitative indication of relative amounts of reactants and products. So equilibrium position, in the process of disturbing the reaction, you may get more product. And you also would get more reactant. But if you add more reactant, the system is going to consume some of that to drive the position to the right. And you still have more of each. But when you generate the equilibrium constant, generate the expression for the equilibrium constant, they still balance because one's in the numerator and one's in the denominator. But the equilibrium position is an absolute. It's more like a capacity factor rather than intensity factor. So the equilibrium constant is the intensity side. Equilibrium position is the capacity side. This came straight out of your book. Right. Okay, so they're good. They are making a distinction. They're not saying it's equal to 1. It's just in the region of 1. You'll have neither right nor left is favored. That's good. I'm glad they did that. Okay. So what's the equilibrium constant expression for this reaction? If you need a methodical way to generate this stuff, well, in this case, we're not saying gas or aqueous solution, right? But we know this one is gas. Actually, iodine at room temperature is a solid. Right? Oh, that's why we say assume no solids or pure liquids. Okay. In reality, this part of the equation would go out because it is a solid at room temperature, iodine. But for argument's sake, we're going to say it's not, and this would be the expression. Then if we do say that it's a solid, you would just remove that factor right there. Oh, okay. I jumped Le Chatelier a little early. It just felt right at the time. So this gives you the description. And when you, this is a good point. Note, in your lab, when you describe what's happening, and you're trying to tell me that products are favored over reactants, you need to have a balanced equation as your reference. Because if you say, move to the left, move to the right, that means absolutely nothing to me. Right? Without the balanced equation, left and right mean nothing. Because if you write the reaction reversed, then your answers are wrong. So when you answer which direction is the reaction going, you need to say, this is the reaction, it moves toward products, moves toward reactants. Okay? We talked about concentration changes, what happens. Right? That's the easiest concept to digest. Come on. This just illustrates the difference between what happens. This is your equilibrium position for the reaction of nitrogen and hydrogen making ammonia. Then if you add hydrogen, some of the hydrogen is going to be consumed, some of the nitrogen is going to be consumed, so that's why this one drops from that position and this one drops from that position and this one goes up. These positions are different, right? But the equilibrium value, the constant, stays the same. Well, here we go. All right, so this is a summary of what the effect of temperature. And in order to draw conclusions about temperature, you need to know if the reaction is exothermic or endothermic. If it doesn't tell you, then there's no way to tell. You have to make some serious assumptions, in other words, before you can determine whether a reaction is going to go to the right or to the left, depending on where that is. Okay, we changed the temperature of this one, right? So at room temperature, this is favored, the blue part. We decrease the temperature, right? We remove some heat from over here, and it drives the reaction toward the pink. Okay, this is exothermic. Oh, pressure, we haven't talked about pressure yet. What happens with pressure changes? The only time pressure matters is if you have gases, right? So this example, gas is here, gas is here, gas is here. So what happens if you say you have a reaction vessel piston in it. Right? And your reaction is here, here, here. Okay? Now, all you're going to do is either move the piston up, move the piston down. So that changes the concentration, right? Because you're decreasing or increasing the volume. So how do we know which way is which? Well, this side has how many moles of gas? 1 plus 3 is 4. So we have 4 on the reactant side. We have 2 on the product side. This is constant temperature, so the heat doesn't matter. So what if we decrease the volume? We increase the concentration. And we give less space available for these, so they go that way. They reduce the pressure by making fewer moles. So increasing the pressure will drive this reaction to the right, whereas decreasing the pressure will drive it the other way. Right? So the total number of moles of gas is determining factor for what happens when we change the pressure. What if we had a reaction where equal moles on both sides? What happens if we move the piston there? What if we bring it down? What happens to the reaction? Nothing. We haven't changed the concentration at all, because the effect on this side is the same as the effect on that side. There's no disturbance. What if, let's go back to this one. What if we pump in helium gas and increase the pressure? What happens then? Nothing. We have not changed. We changed the pressure, but we haven't changed the relative amounts of either side. So nothing will happen if you pump in an inert gas. It's not part of the reaction, right? Okay, that's pressure. What happens to the equilibrium position if we introduce a catalyst? Well, we know if we introduce a catalyst that's properly designed for the reaction, we get an increase in the reaction rate. But does that only affect one direction? It affects both directions. So the reaction rate forward and reverse are still balanced, even with a catalyst. It's just that the reaction proceeds faster. So the equilibrium position is not affected at all with a catalyst. Let's see. Oh, we did concept questions. All right. I thought we were going to talk about, I didn't have slides in there for that, where we have multiple types of reactions. Check out your homework, and when we do our review, there should be some questions in your homework that will lead to questions of whether it's multiple types of reactions. And then we can hash that out during review. In this reaction, something is undergoing reduction to something else, while something is undergoing oxidation to something else. We can fix this one pretty quick. Potassium doesn't change. Oxygen doesn't change. Sulfur, maybe. Nope. Sulfate here, sulfate there. Sulfur doesn't change. So chromium will change. This is 6 plus. Right, we did that one earlier. How about this one? So if this is going to be 3 times 2 is 6 minus, that means that this overall molecule has to balance that. That means this is plus 6, that's plus 3. So chromium has been reduced from plus 6 to plus 3. And hydrogen, oxygen didn't change, so carbon must be changed. So we're going to go from this one to that one. Where's the 3? This is ethanol. That's this is acetic acid. That's a different way to write acetic acid. We've written it like this, right? That's another way to write it. There's your 2 carbons. There's your 3 hydrogens here. There's your other hydrogen there. And there you 2 oxygens. That's just another way to write acetic acid. So what has changed? Carbon has changed. This one's difficult to deal with. Carbons are really tricky to do, and if I put one on your exam, just tell me about it and I'll throw that one out. Because it's not something that we need to be dealing with right now. Come on. Here we go. All right. So what we're saying is the carbon has changed from -1 here to +3 here. So the carbon has been oxidized, that state. This carbon didn't change. It's still the same carbon as before. But this carbon did change. All right. That's probably enough for our brains for one day. How about your lab? Were those the only questions you had?
Yeah, I'll try to finish it up tonight and turn it in, and then I'll turn in that one of the ideas too. I'll just scan them. See what those are.
Okay. Sounds good. So let's stop this thing.